What's your name?
John.
Okay, well, bye.
Bye, Isabella. Hey, did Nina ever say what she wanted in the book report? Like what she wanted it about?
Yeah, she put 600 words or more on how this book applies to you.
That's good.
Yeah, I know. Due September 22nd.
I'm sure to post more details as it gets closer as well.
Yeah, I'm sure there will be. I haven't started reading it yet. I really need to. I just got it in yesterday. But I don't know.
I should have made breakfast with those extra time. Now I'm starving.
Slacker.
I guess I'll put it on mute, Karen. That's not what I wanted. Actually, that works out. Doesn't look like I'm muted. Okay, good. Hey guys, sorry, I thought today was Thursday. So I kind of wasn't prepared for
I mean, we could do this Thursday. That's fine.
and we have to do 4 hours. So I have, let me share my screen. Oh, not that. Share screen. Okay. So last night I kind of popped my head off of the bed and I said, oh my God, I think I said something wrong. Not a huge deal. I mean, I could fix it now if I did say something wrong. But so just a really quick mop up from yesterday in the vascular talk. Let's see. And this is a hard point anyway, so it's worth going over really quickly, and then we'll get back into chapter 3 where we left off. Actually, we'll maybe do a little review in chapter 3 because review is always a good thing. Sorry, I gotta speak a little quieter. Yesterday we talked about Bernoulli and Poiseuille, and so Bernoulli, we talked about how there is a conservation of flow over here on Bernoulli's side just in general, if 100 milliliters per minute in equals 100 milliliters per minute out, conservation of flow. And in order for that to happen, velocity has to speed up considerably in the narrower portion in order for that conservation of flow to occur. And then the trade-off is a loss of blood pressure. All right, so I think that much was clear. Well, I mean, clear as mud. I understand this is not always easy concepts, but I think I said something. Here, the Poiseuille is all the way down here, and I can kind of do some review on, well, what is it? I guess Tuesday next week. We only have this once a week, this particular class. But I wanted to say this now. So one, that I didn't forget, and two, let's just get rid of some of this stuff here. Two, I wanted to make sure that you're not spending a week thinking that I said something wrong. Now, what I might, this is what popped my head off the pillow last night. Volume, the conservation of volume flow. So of volume flow still exists in Poiseuille's equation. So once again, milliliters in, it has to equal milliliters out, milliliters per minute, and it has to equal milliliters per minute out. There's no invention or you can't possibly have more going in than you have coming out. If you did, then you'd have a leak. However, the volume flow, it looks like I think I did say this correctly. Volume flow overall decreases, but that means it decreases over here, it's decreased here, and it's decreased here. In other words, because this is a long stenosis, the body physically, the mechanics wouldn't allow an increase in velocity to maintain, let's say 100 milliliters per minute, on this side, and then in the middle, and then on this side. What instead happens is everything has to reduce. So instead of 100 milliliters per minute, let's say it's been reduced to 50, which means it'll be 50 here and 50 here. Now we're talking about volume milliliters per minute. So the volume flow has to decrease all the way across. In Bernoulli's, the volume flow is maintained, but there's an increase in velocity. On this one, this is essentially a very long stenosis from here to here. Bernoulli's no longer is works. And if you think about it, so on a garden hose, you put your thumb over the end of the garden hose, you create a stenosis, and now you're able to spray your garden or whatever. However, if you instead you took the entire length of that garden hose and decreased its radius or decreased its inside diameter, the overall friction against the walls would be slowing everything down to the point where it really, everything has to slow down. It just simply cannot make it through as fast. So that's the difference between these two. Volume flow is maintained, or the conservation of volume is maintained in both equations, but the overall volume has to reduce in this situation where you have a very long stenosis. Okay, I think that is where I wanted to be. Okay. Well, I might as well just continue to use this. Come on. Why aren't you getting any bigger? Okay, well. Sorry, like I said, I was kind of, oh, such a pretty picture too. I gotta get some kind of automatic calendar to, actually, let's get this back down to a reasonable size. Okay, so back to chapter 3 and doing a little review. Actually, before we start, let's see, what else did I want to talk about? I'm supposed to have each one of you with your video on. As of right now, I'm not requiring it because I have nowhere on my screen to put you guys. So I can't see you. I can't see you regardless. I have to remove the images of you. If I get my second screen working, then I will have a place to put all of your beautiful faces. At that point, I will require video, but until then, we're holding off on that. And that's actually, it's not just a PEMA or my requirement or a PEMA requirement. It actually goes all the way back, all the way up the line to the Department of Education on distance learning. You're supposed to be able to see each other. But don't worry about it just yet. I can't see you anyway. Oh, and the other thing is, having a real hard time remembering to put the asynchronous assignments out. So today's asynchronous assignment is going to be really short, shorter than the other ones. And like my daughter has the same thing in her school, and one of her asynchronous assignments was, were you here today? Were you here on August 26th? I might make it that simple, just because we have to do something every day. So I'll do that after class today. Those of you obviously who are not in lab have to do it today. And those who were in lab, you can do that on Friday. I'll put that again.
They already have their thing for today because this is their first absence.
Right.
So the new one will be tomorrow.
Oh yeah, you're right. The second asynchronous is on Thursdays. You're right. Awesome. Oh, good. Thank you.
I'm confused now. I thought we already had 2.
I know. Apparently, I'm confused too. No. For this week, I've assigned 1. I assigned it on Monday. Half you do it on Monday, half you do it today, and then I don't even know who spoke. You're right. The second asynchronous assignments I put out on Thursdays. I'm gonna have to create a whole schedule an electronic schedule for just pellet me with reminders every single day, because I'm more confused than you guys are. Trust me on everything. Okay, let me, go away. Go. All right, I have to move this down because the Zoom controls keep getting in my way. I'll put the scale over here because that is how our ultrasound machines usually are. This is a 0. I don't like that 0. Let me zoom in a little bit. Ah, forget it. Wasting time here.
Just on the right page, we're doing what, chapter 3, or we're going to chapter 4 now?
We have not finished 3, so we're still in chapter 3.
Okay.
Let's see. All right. So just really quick review. 1 cycle is up, down, and back. Period. So time, and in fact, we'll put a T here for time, is from here to here. The time for 1 cycle is period. Determined by the sound source, not adjustable. With my fingers crossed, not adjustable. It is adjustable. It's just not adjustable without pausing the machine. But just remember, it's not adjustable. That's me explaining too much and possibly confusing the issue. 0.6 to 0.06 to 0.5 microseconds or millionths of a second so for the time for one of these cycles to occur is in the less than a millionth of a second. And that's that. That's all I want to talk about. That's all I want to do is review. And so this is, once again, that's period. I need screen to be a little more. Okay. Bouncing around on me. Okay, and then frequency is, well, I actually, technically speaking, the frequency, if this is 0 seconds, and if this is 1 second here, then technically my frequency is 1, 2, no, that's not a full cycle. That's only half a cycle. So technically 2.5. Does that make sense? It's not a full cycle. It's only the first half of the cycle once we got to this 1 second mark. And therefore, what is going on with my pen? I understand what's going on, but I'll have to fix it later. Okay, so that's our frequency. Frequency, again, not adjustable. Frequency and period are very closely related. In fact, they are reciprocals of each other, meaning if our period goes, or my frequency increases, my period decreases. Let me draw that really quickly. Let's just do this. Well, I didn't want a red line, but that's what I got. So I could start off with a frequency that looks something like that. Looks like the same frequency, 2.5. And my period is from here to here. if I increase my frequency, my increase in frequency, 1, 2, 3, 4, 5, 6. But now my period is from the beginning of this one to the beginning of that one. It's, well, according to just the way I've drawn it, looks like about half. So that's my, this is my, well, my period T. It's also my wavelength. We're just talking about period now. So that has gone down as my frequency has gone up. All right, should make sense there. Typical imaging frequencies, 2 megahertz, in other words, 2 million hertz to 15 million hertz, megahertz. And so, yes, they are reciprocals of each other. So hertz is per second, and for what we usually are dealing in kilohertz or thousands per second, and we also deal in megahertz or millions per second. And for us, this could be any event for us we're talking about. Well, when we're talking about millions, we're talking about the millions of cycles per second. So if we have, from here to here is 1 cycle, millions of those per second occur in ultrasound imaging. When we talk about kilohertz, this is, you know, we're not dealing with this yet, but kilohertz is in our pulses. So if you've ever heard of a dolphin or a whale, when they're tracking a fish or they're trying to figure out what a fish is, you'll hear click, 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 click. That is a pulse of sound. It's not the frequency, it's how many times they're clicking per second. So we in ultrasound click thousands of times a second, but our frequency is millions per second. They're not the same thing. They seem like they would be, but they're not. Clicks versus the actual waves are different. Okay, hertz. The bigness parameter is power, amplitude, and intensity. We talked about that, right? Yes, we did. So our amplitude, let's go back up to this guy here. Yike. Oh, yeah, I'm a little too close here. Okay, so amplitude, of course, is usually measured simply from the baseline, which is 0 watts, 0 decibels, to the peak of the sound. We can also measure, we put an imaginary line across here, and we could measure a peak to peak, so-called. And of course, this number, whatever number this is over here, would be double this number because we're measuring peak to peak, so it's twice. But this is more the way, it's just simply amplitude. Okay. Power, remember, is proportional to amplitude squared. Okay, so that was a really quick review. If you guys have any questions, go ahead and, oops, dang it, that's not what I wanted. I've realized that this is electronically speaking, this is a large canvas, and I've used the entire thing, which is why some of my writing was really ugly. I didn't think about how, so I'm going to zoom in a little more this time. The letter P, brought to you by the letter P. Okay. Intensity. Oh, I did talk about intensity, didn't I? Because we talked about the flashlight. If we have a wall and I were to shine let's use, yellow, because yellow is a nice color of light, right? And I have one flashlight, it's putting out 10 watts. 10 watts of light, and I've focused the beam so that, well, I unfocused the beam really so that it is wide. And then I focus the beam, still using 10 watts, but I focus it to a small point on this wall. So which light is more intense? Anyone?
One on the
Yeah.
right.
A small one, yeah. Which one has more, which one's using more power?
The larger one?
It's a trick question.
Gonna be
Neither.
this
It's the same amount.
Yeah, neither of these are using more power. These are both, this is 10 watts, 10 watts. So the intensity is increased simply because those 10 watts are now concentrated in a smaller place. So I think I mentioned this, but I don't think we got into it. I certainly don't remember writing down this equation. All right, we're going to get rid of yellow because it's hard to write with. Intensity, and we're going to do watts per centimeter squared. Centimeter squared, because it's not simply one dimension, it's two dimensions. It's like height and width versus little tiny height and width here. So intensities in watts per centimeter squared is equal to the power in watts. And we, for the fun of it, we just said 10. Divided by the area in centimeters squared. It's squared because that's how you find areas. So remember, we don't even have to throw, let's not even throw numbers in here. Just remember that if you increase the denominator, you decrease the product here. So I increase my area. Let's see, that'll basically look like this. If I increase my area, I decrease my intensity. And of course, opposite is true. If I decrease my area, I increase my intensity. I put that 10 watts into a smaller spot. And of course, power is power. If I increase my power, I'm going to increase my intensity. Anything in the numerator is directly related to the product. Anything in the denominator is indirectly, or you know, if it goes up, the product goes down. Let's see. Clinical imaging intensity ranges from, and that's crazy. This is a huge range, it seems to me. 0.01 to 300. That can't be right. Watts per centimeter squared. Clinical imaging intensity. All right, well, you might feel some heat. 300 watts per centimeter squared seems like a lot. I'll have to double check that. I'm sure it's correct. Anyway, so those are your range. Let's see, is this adjustable? Well, yeah, it's adjustable. We adjust, oh, let me ask you guys, and we've been doing knobology. How can we adjust the intensity? There's two ways in particular that I'm thinking of.
Frequency?
What's that? Frequency. No, not, well, in a very roundabout way that can change it, but let's stick to these two.
So we narrow our focus down?
That's one of the things. So our little focus guys, these little arrows, little sideways triangles on the side, when we change our focus, we are quite literally taking that beam of sound and focusing it at that area. That's why we change the focus. And by doing that, we actually see more detail at that focus. But it increases, well, I'm sorry, it decreases the area right there at the focus. The area is decreased, therefore the intensity has increased. And then the other part is our power. And we do have control over the power button. Honestly, I pretty much never touch it, but that is the other possibility, is turning the power up directly increases intensity, or turning the power down directly decreases the intensity.
Can we do that while it's scanning, or do we have to pause it first?
Yeah, we can. It is so yes. So according to the book, that's how they say it. It is adjustable. So okay. Yeah, you could do that without pausing the machine at all. Let's see what else we have with this. We have the amplitude, power, intensity are three parameters that describe the magnitude or strength. These parameters tend to therefore how is intensity related to power and amplitude. Okay, so let's move this back a little bit so we can see that. So I want a pretty color. Pretty color. Let's do purple again. Okay. Intensity is proportional to the little Jesus fish there is proportional to power. So, which basically means if you increase your power by 5, whatever 5 is, 5 watts, you'll increase your intensity by 5. So yeah, so when the wave's power is doubled, the intensity is doubled. When the wave power is quartered, the intensity is quartered. Intensity is also proportional to amplitude squared. So when a wave's amplitude is doubled, the intensity increases to 4 times its original value. Well, that makes sense, because didn't we also say earlier that power is proportional to amplitude squared? So it makes sense that since we just learned that intensity and power are equivalents, directly related equivalents, directly proportional equivalents. And power, we learned the other day, is proportional to yeah, are you here right now, Bree, or? Sorry. Power is proportional to amplitude squared, and therefore, since power and intensity are equivalents, intensity is proportional to amplitude squared. That was a mouthful. Okay. Wavelength. Now, it's kind of like I can't wait to get to wavelength, because it's one of the more important ones that we talk about. And I started to give you the an equation yesterday, and then I kind of stopped, but I'm like, oh, why am I giving you the equation now? I don't get it. Kind of threw myself for a little loop there. Get our baseline down here. I'll put the scale over on this side. And let's do a nice color for the wave, blue. Do it again. Okay. So just like period, where we measure one cycle, wavelength is also the measure of one cycle. So let's just put it below here. Wavelength is signified by lambda. It is the length. So before we were measuring the time, now we're simply measuring the length of this cycle. And you measure cycle length. Does it mean that, could I measure it from here to here? Of course, it's the same difference. But we just don't make a habit of doing that. We prefer to measure the cycle itself. Wavelength is measured in units of millimeters, meters, or any other, in our case, millimeters. Typical clinical is 0.1 to 0.8 millimeters. Wavelength is determined by both the source and the medium. Ooh, now that's interesting. So the source, well, the source we already learned, did we? Yes, yeah, right there. We already learned that the source determines the frequency. Now here's something that really, I didn't understand this for the longest time. And finally when I started teaching ultrasound, I was like, oh, wow, that makes sense, kind of. Frequency is determined by the source. How many cycles per second is determined by the source. And I used to think that frequency and wavelength were a set. If the frequency is 100, then the wavelength is a certain number or a certain length. That's actually not true. Depends on what the medium is. And so the frequency doesn't change crossing our fingers and saying it doesn't change. It actually can change, but the frequency goes from one soft tissue to another, or it goes from air to water, or air through a prism like glass. Well, I'm confounding light and sound, but they actually are the same when it comes to frequency and wavelength. The frequency is determined by the source, and wavelength is equal to the speed of sound over the frequency. So the frequency is important in determining the wavelength, but then so is the speed of sound. So the speed of sound, basically as things go faster, it literally stretches out the wavelength. And as things slow down, let's say it goes to a different medium and it slows down, the wavelength is squeezed together. The frequency doesn't change. The amount of times per second doesn't change, but the length of the waveform, the wave does change. Is this adjustable? No, it's not adjustable on the fly because, let's see, give me red. Because we already determined that frequency is not adjustable. So if you as a technologist can't adjust frequency on the fly, without pause, then you cannot change the wavelength. C, remember, stands for constant. We're assuming a constant rate of speed. Speed of sound actually is anything but constant. But we have to, just for mathematical reasons and for reasons of developing these machines, we have to assume a constant. So the wavelength is not adjustable. Typical measures. And so I'll start to talk about the speed of sound. Once again, I'm drawing too large. That's okay. I'll just zoom in over here and use this little section. Okay. So we already mentioned wavelength. Oh, I have a little, yeah, we'll do that. Ugh, I don't like red. I don't like drawing with red, it's ugly. Okay. Wavelength then is equal to the speed of sound over frequency. The speed of sound, in general, is always assumed to be 1.54 millimeters per microsecond. So it doesn't sound like a lot. Well, I have it written. Yeah. Yeah, no, that doesn't sound like 1.54 millimeters. Millimeters is a tiny little thing, and so we're talking a millionth of a second. A millionth of a second is a very, very small number, and so a very small amount of time. So actually, this is lightning fast inside the body, and sound really does travel quite fast, faster than you probably think. And I'm just going to use one of the numbers I already have written. Let's say my frequency is 5. Now this depends, right? We have different transducers that have different ranges, and with each transducer you have different settings. So we're going to just say 5 cycles per second. Well, oh, yeah, 5. I'm sorry. I'm having a brain freeze here. We're talking about ultrasound, so megahertz. 5 million times per second. Oh, and that's right. Remember on day one, when we go back to that chart on chapter 1, page 6, and the chart below, it says that, by the way, mega and micros are complementary metric units. So mega is 1,000,000. Micro is a millionth, 0.1256. These guys, mathematically, I gotta tell you guys, I don't fully understand this because you guys know that when you have an equation, if you have millimeters on top and millimeters on the bottom, you cross out the millimeters, right? We all know that. But the complementary units, we also cross out. So this guy and this guy are now crossed out. And the only thing we're left with is millimeters. Well, that makes sense because our lambda is going to be in millimeters. So our answer to this one, by the way, so lambda, wavelength in millimeters. Well, I don't have to write that there. Lambda equals, what was that? Oh, that's right. 0.31 millimeters. So in other words, our wavelength from here, up, down to about there, is 0.31 millimeters. Now, one thing I would do, yes.
Could it be, since they're complementary and we multiply by the reciprocal, that 10 to the -6 times 10 to the 6th equals 1?
Yeah, so if you were to solve, if you multiply by the reciprocal, then the reciprocal would, so 1,000,000 becomes 1,000,000, and vice versa. Yeah, that's mathematically, I think you're right. Is that what you mean?
Yeah, that's what I mean. Because I just put it in on my calculator and it becomes 1. So that's why I was wondering if that's why they get rid of it.
Yeah, basically, yeah, it's reciprocal. So I guess.
Mr. F, I'm so sorry. You sound like a robot or like Darth Vader or something. We can't understand you. At least I can't.
Is that other people too?
I can't hear it either.
Yeah, that's for
I have no
everybody.
idea what you said. I think it's for everybody. I thought
Yeah,
it was
it's
just me.
Yeah, it's for me as well.
me as well.
Oops.
I hate to jump back in. Can you hear me? Can you understand me now?
It's still like it's being put through a
Nope.
mechanical filter. Just turn off your mic real quick and then turn it back on, see if that fixes it.
I think this is it. How do I sound now? You better.
Nope.
It's still the same.
Nope.
All right.
You might have to go off and come back on.
Yeah.